2024, if I can take it mic, that's good. So I obtained my MSc at EPFL in 2024. Then I went to work for ChainSecurity, which is a smart contract audit firm, and Randomu, which works on threshold cryptography. And the work I'm going to present today was my master thesis for this this degree. And so to jump into it, I like to use the title as a way to explain it. So what is commit and reveal? Commit and reveal is a cryptographic protocol that we can use to put a message in an opaque envelope and then give the envelope, and later we can take out the same message from the envelope. Of course, there's a real life equivalent to this, which is the ballot box. So usually I bring a physical one, but this time around there's not a votation in Switzerland. Can you believe it? But so you get the picture. And to use this to understand what we get out of commit and reveal, we get these two properties. We can commit and we can reveal. And we want the message to be, the commitment to be hiding, which or the envelope to be opaque, which means that the message is not revealed when we have the commitment. And we also want it to be binding, which is the fact that the envelope is sealed. You can't change the message and then reveal a different message than the one you decided on when making the commitment. And the other question is commit and reveal for smart contracts. How do smart contracts use commit and reveal today? I will show you 3 examples. The first one, you might have seen the screen, is ENS registration. When you go to register, you do 2 transactions. First transactions is committing to the name you want to register. And the second transaction is revealing that name and registering it that way. And the reason you do it that way is to prevent an instance of front running. So front running is the fact of putting a transaction in front of an existing transaction based on what the other transaction contains. So an intuitive phenomenon that sort of breaks the causality, because the cause happens before the effect in the final ordering of the chain. And in the specific case, what could happen is you go to register Julie.eth. Someone sees your transaction and goes to register it in front of you, and then tries to say it back to you for a premium. So we don't want that. That's why ENS uses this commit and reveal scheme. Another instance of commit and reveal in smart contract is also ENS, which is the ENS auction that they ran in 2017, if I remember correctly. So at that point, most of the names went out at once. And to attribute them, they ran a second prize sealed bid auction. And they used commit and reveal to implement that. So you would commit to your bid. Everyone could commit to their bid during a certain period. They would have to put more than their bid in a smart contract to hide the exact amount. Then later people could reveal their bids, and the highest bid would get the name. Now the interesting thing with that is that it's not very capital efficient, because you have to lock your money in a smart contract for a while, and we're going to come back to that. And the third example I want to show is gathering randomness. It's a very old idea in blockchain called RANDAO usually. And it's the idea that you have multiple parties who will contribute to the randomness. So everyone commits to a number, hopefully a random number. Then in a second phase, everyone can reveal that number, and hopefully the resulting output will be random enough. Now, commit and reveal schemes, simple commit and reveal schemes have multiple limitations. They take 2 rounds to resolve, commit and then later reveal. They have to deal with unrevealed inputs in a way or another. If a party gives you a commitment and it decides not to give the reveal to you, and they are prompt to timing games, because the last person to commit or to reveal can sometimes have more information than the first one. So you have an incentive to try to do it at the last minute to get this asymmetric information. Now, how does, for example, the Beacon chain, the Ethereum Beacon chain, uses this RANDAO? They sort of solve this problem a little bit. So they use BLS signatures and VRF, so they have only 1 round. If you don't reveal your input, you have to skip your block as a validator, so you lose a bit of money. And there are some timing games, but they're sort of mitigated. This is a whole topic I'm not going to get into, but it's worth mentioning that they are doing that. Now, the impetus for the research project was, there must be a better way to do this, and we should study that at EPFL. So, coming to it, what I did at my project is I put a system of delayed execution in the execution layer. And using this system, I run simple auctions. And I compared this to the baseline, which is commit and reveal in contract. And also the academic stuff, prior art, literature, and everything like that. So what would be the expected benefits of a system like this? Well, you would get, for once, front-running protection, which is nice. You would also limit the ability of the block builder to front-run transactions and rearrange transactions because they cannot see the transactions while they are not revealed. And you hope to get capital efficient sealed bid auctions because commit and reveal sealed bid auctions have this locking up a lot of capital for a while. So to formalize this a little bit, I took from the yellow paper the way that they describe Ethereum transactions. And non-Ethereum transaction is processed when you can put your transaction in this state transition function that produces the next state of the blockchain, like that. And basically the block proposer can decide what transactions it puts in which order. What we proposed is maybe we could have the same thing, but with a security property, which I call causality, which is the idea that nobody can go and alter the previous state having been revealed the transaction itself. So that's interesting. And a second property that we're looking into is if we try to generalize this model a bit to multiple inputs and not just one transactions, you would hope to have something like fairness. The fact that people cannot cancel their input or change it after they've seen other people's input. Now, I use two variants of cryptography in this project. One is threshold decryption. So the idea that there's a committee with maybe 10 nodes, and any 7 of these nodes are enough to decrypt a given message, but not any 6. And time lock puzzles, which are these computations that take a long time to perform so that you can say, okay, I put my message in a time lock, and I know that it's going to take at least 10 minutes for anyone to hopefully decrypt. Now, to discuss the results a little bit, so I will answer these questions. Did we achieve the security properties? We argued that yes, because you can read the rationale, I guess. I don't have much time. So how do we compare the different variants? So here's a summary for threshold decryption. In short, it makes the blockchain execute a bit more computation compared to the benchmarking we've done for the VDF, so 192,000 gas. It's consistent with the EIP 1108, but it adds 200 bytes roughly a witness size. If we look at VDFs, we have the opposite. We have more data that needs to be shared, but we have less execution because the verifying the verifiable delay function happens to be a bit faster in this instance. So to put this in a table here. And so what does it look like from the application's perspective? Well, the nice thing is we've solved the capital inefficiency for auctions, that's for sure. We know that we've decreased throughput because in any case you have more computation that needs to be done, so naturally the throughput given the same amount of gas will come down. And in some points of view, we've increased the latency because you won't get any sort of result of the execution of your transactions until they go through the whole process. Whereas if you just include a transparent transaction in a block, you know that you already have the final results of the execution when you see the block. And we've messed a little bit with the ability to simulate transactions off-chain because your transaction will only execute after the entire queue of encrypted transactions that are still waiting have executed, and you cannot simulate those by design. So this has the problem that it kind of breaks the gas estimation that you have in your Ethereum client. This is something I've noticed while experimenting with that. But it also breaks a lot of MEV extractions, good and bad. Now, some design choices that I did in my project. So maybe the most important one is that I started from the idea that you need a hard fork to introduce delayed encryption into an Ethereum-like blockchain. So I think to fully do it, you do, but I will go back to this, there are ways to do it in a more incremental way. I put every transaction in the encrypted queue. There's no way to do a transaction that is faster than others. And this is good for auctions because if you don't have, if you have a fast queue, you might be able to cancel your bid or do stuff that influences other transaction, and you would not get the causality property. But for certain transactions, certain applications, this might not be good. So maybe one thing we could have is we could have a fast transaction queue and a slow transaction queue, and the fast one can be unencrypted. But there are, of course, implications to that as well. And we were only able to encrypt the call data, so the message you sent to the smart contract, not the sender, for example, because you need the sender to make sure that the sender has enough gas to pay for transactions. But maybe there are ways we can do that. Maybe we can use ZK proofs to prove that the transaction is solvent. And you also have, we didn't experiment with TEs, but for some trust models, this might be a valid application. Now, design choices in Ethereum itself that can interfere with the front-running protection. One is the fact that you expect to only pay the amount of gas that you used and not the amount of gas that you reserved. But that means that at some point we need to be able to execute your transactions. And there's some attacks on encrypted mempools where you reserve the entire block, but you don't actually use it. And that just blocks everyone else. So this is a bit difficult to deal with. It also breaks a bit EIP 1159, which is the burn and the adaptative base fee. But because you need a feedback loop from one block to the next to know how much gas was used, and you can't have that if all the transactions are encrypted. It also interferes with EIP 7702 recently, which is interesting because I used the fact that Ether cannot leave an account unless that account does a transaction to make sure that they would still have enough gas to pay for the transaction when it goes through the queue. But with the EIP 7702, this logic can break because you could empty an account while it has transactions already committed but not executed. And the question is also, what about the reliability standards that Ethereum have? Maybe we don't want to have a threshold network that can hold or deny some service to the blockchain. So this is always a valid question to ask. Now I want to highlight this document published by a bunch of people I've been able to talk to, which is called the Road Towards an Encrypted Mempool on Ethereum L1. In particular, they have a lot of interesting out-of-protocol solutions that don't necessarily require a hard fork, which is something that I was not able to experiment with because of time as well. And I think I think there are a lot of what I presented is found in this document. There's also more interesting research in that space. So just shout out to Mark from Nethermind and all the Shredder people, and there you go. I want to also acknowledge these people who've been very helpful in my project. That is Professor Brian Ford at EPFL, Jolan Romeyer from Randamu, and my colleague Shufan Wang. I will give you a link with the slides, the report, the code for the project, which if you want to run the auction yourself, you can. And I'm waiting for your questions. No questions? This will be on the test. Not yes, so not in production. It's a academic prototype. There's something that would be trivially broken if you put it in production. So that's the thing. If you want to play with the encrypted transaction, you should look into Shutter, the Shutter network on Gnosis chain. I mean, it also has some issues, but that's because it's not in protocol. So I mentioned TEs. How can TEs be used in synergy with what I presented? I think TEs can custody a decryption key by nature. So you could have, one example is you could just have the TE decrypt encrypted transactions on time. Another maybe interesting thing is you could combine threshold networks with TEs. So you have multiple TEs that have to cooperate to decrypt the transactions. And this is maybe a good idea because if you have only one TE, you can isolate it from the network and lie to it about the state of the blockchain. Whereas if you have multiple TEs, it becomes harder. So it's not a TEs versus threshold network. It could be both.
Do you have any other questions? Okay, thank you very much.
Yeah, thank you for your attention, and I'll be outside if you want.